All right, so our second speaker today is Alan Chang, and he'll talk about Euclidean distortion of quasisymmetrically Hilbertian metric spaces. So please.
Thank you, Mario, for the introduction. Thank you to the organizers for the invitation, and thank you all for being here. And so today I'll talk about a metric embedding question. Um, and so I guess for a certain class of metrics or metric spaces. So I'll begin by, I guess, stating like a general question that this is a part of, which is that if you have a metric space, XT. I guess for us, in this talk, we'll only talk about finite metric spaces. So you have a finite metric space, and let's always let little n denote the cardinality of our space. So then the question is, how well can we embed this space into some other space? And the ones we care the most about in this talk will be L2 and L1. But you can ask the same question for LP or for other spaces. Uh, yeah, but for us, the focus will be L2 and L1. And so I guess one way of measuring like this question of oops, what I used to so yeah, one way of measuring like, how well um, like a space embeds into another space is in terms of the distortion, right? Or the by-Lipschitz constant. So we say XD embeds into LP, or I guess this works for other metric spaces too, but let's just stick with LP with distortion D. Okay, this statement means that there exists a map phi from X into LP, which is by Lipschitz, and the ratio of the upper and the lower constants is D. So such that for all xy in X, if you look at phi of X minus phi of Y, LP norm, right? I guess you can, I'll write it like this. So I'll make the upper constant 1 and the lower constant 1 over capital D. Right? Just because this is how things will be. Well, at least in some of the examples I'll give. Right? But of course, you can move this D to the other side. You can multiply by some other constant or so on. The important thing is the ratio of these constants. Um, and so one fundamental result in this area is a theorem by Bourgain from the 1970s or something, which is that so for this, yeah, so for a finite metric space, um, right, so any finite metric space embeds into LP with distortion. The distortion. Right, so the idea is that right, the larger the space is, the worse things can be. But everything's finite, so there's always at least one embedding, like, at least one bi-Lipschitz embedding. But yeah, it goes to infinity as n goes to infinity, and but it's the rate at which it goes to infinity is bounded by a constant times log n. Mhm. So this is this fundamental result. I guess you can say more about this too. Like, so I won't really mention dependence on p because we only care about p equals 1 and p equals 2. Um, but if you're interested, like as p goes to infinity, the constant actually gets smaller because for p equals infinity, you have the Kuratowski embedding, or you have a isometric embedding in that case. Yeah, but we care about L1 and L2, so very far from p equals infinity. Um, so this is Bourgain's theorem. Yeah, and so it's the remark is that this is sharp. Like this log n cannot be improved. And the kinds of spaces that attain this sharpness are expander graphs, like constant degree expander graphs. Um, um, yeah, so if you try to embed those into LP, you have to have distortion at least constant times log n. Um, okay, so in other words, Bourgain's result is sharp, and it seems like nothing more can be said. Um, well, at least about general metric spaces. And so this is why we're interested in in trying to improve this log n in the case of specific like more like metric spaces with additional structure. So if we make some assumptions, uh, on our space, uh, can we improve? Can we improve the log n or like lower it? And I mean, this is a very vague question. Obviously, you can make some trivial assumptions that will trivially lower this log n. But so there are many directions that this can go in. So one way of thinking about the question that we study, the class, well, it's in the title, like these quasi-symmetrically Hilbertian metric spaces. And so one motivation for this is to actually look at an application of Bourgain's theorem to a computer science problem. So I'll take a brief detour and talk about that, which will motivate the kinds of assumptions like, that we'll make. Oops. Yeah, um, so to explain what kind of assumptions we make, let's talk a little bit about the sparsest cut problem. So are there any questions at any point or any stop me at any point if there are any questions. Yeah, so the sparsest cut problem is a problem from graph theory. And you have a graph, there's the vertices and edges. Just draw a simple graph. Okay, something like this, right? And and then the idea is for any subset of the vertices. So for example, if I take this one, and this one as my set S, I can define the cut set of the edges that are cut by this subset S. So let's say E as complement for my notation. This is the set of edges. Edges are unordered, so pairs XY in E, such that one of them is in S and the other one is in S complement. Okay, so in this picture, what is my set of cut edges? This one, this one, this one, this one. Most of them. Okay. Yeah, all of these um, are are part of my cut set here. And so there are a lot of variations of questions you can ask about this, right, that have applications to, well, I guess to the real world or to networks or whatever. Like for example, you might want to minimize this given some constraints, and there's some version of that called the min-cut problem. But the sparsest cut problem is slightly different. So the sparsest cut problem asks, so let's say SC, the quantity we're trying to find is, so SC for sparsest cut, we minimize over all subsets of V, the cardinality of this cut set. Okay, there's going to be more. Because if you just want to minimize this, you just take S to be the empty set, right? Nothing's very interesting. But the thing about the empty set or if you take S to be very small, right, then most likely very few edges will be cut. So you want to penalize that by dividing by the cardinality of S. And because this quantity, this cut set is symmetric between S and S complement, you also divide by S complement as well. I guess usually the way the problem is stated, instead of having the product of these two things, you divide by the minimum of those two, or sorry, the minimum. But they're equivalent up to a constant. Everything we talk about this will be up to constants anyways. Yeah, so this is the quantity we want to find. I think this has some interpretation as like some kind of like discrete isoperimetric constant for the graph, right? Because the top is like the perimeter, the bottom is like the volume. Uh, so that's what this can be interpreted as geometrically, some kind of yeah, isoperimetric quantity associated to the graph that we have. But for the applications, right, people want to compute these things, but it turns out that computing this is NP hard. So so that means that there's no good polynomial time algorithm for this unless p equals NP. And so So we want to seek some way of approximating this, and that's where these ideas of metric embeddings come in. Okay, so yeah, how is this related to metric embeddings? So first, how is this even related to metrics? So the idea is that we can express this quantity here as in terms of some specific metrics. So there's something right, there's called, so given a set V, so this has nothing to do with the graph right now, what I'm going to say. Okay, so given a set V, given a set V and a subset S of V, you can define the cut metric, let's say D sub S on V, right, which is just, so 2 points, let me write it down here. This indicator function of S applied to X minus indicator function applied to Y. Right? And this is just it's just 1 or 0, depending on if they're in the same component, like well, if they're both in in S, right, then it's 0. Or if they're both in S complement, it's 0. And okay, if one is in S and one is in S complement, right, then it's equal to 1. Okay, it's not really a metric, right? It's a semi-metric. It doesn't satisfy the non-degeneracy. But I guess we'll just call it the cut metric. Right? So this has nothing to do with the graph, right? You can do this for any set. And the observation is that this numerator that we're trying to in this quantity we're trying to minimize is just summing over all edges. So this is where the graph actually comes in, right? You sum over all edges. I use the braces. Sum over all edges of this cut set, because that's exactly counting like the pairs x, y, where one of them is an S, one of them is an S complement. So that's the numerator. And then for the denominator, notice that this thing is actually just if you sum over all pairs of vertices of the same thing, right? Because yeah, I guess you just pick one up every time you have x is an S and y is an S complement. I guess here x and y are ordered, so you need a factor of 2, but that's okay. Yeah, so the Sparsest Cut problem is can be viewed as the following. Okay, so ignoring this factor of 2 here, so you minimize over all these, which are cut metrics on V of this quantity. So you sum over dxy, where you sum over edges, and then in the denominator, you sum over all pairs of vertices of the same thing. Okay, so it's just a reformulation of the question. Okay, but then the idea is, so this is, it's equivalent to the original question, so it's not any easier. The idea is that we're now going to consider a different version of this. Let's call this SC prime, where instead of minimizing over cut metrics, you just minimize over all metrics. So these are cut metric on B. Sorry. Yeah. So here we minimize over all metrics, the same quantity. Right? And well, it's clear by definition, right? We're taking a minimum over more things. So SC prime is less than or equal to SC. So that's one observation. Another observation, okay, this is a little bit, it's not as straightforward to see, but SC prime, this one can be solved, can be computed efficiently, like in polynomial time, with linear programming. If you rephrase or if you rewrite things, like you homogenize so that the denominator is equal to 1, and you check the conditions, right, we're minimizing over. So the constraint is that these are metric, but those are all linear constraints. And the top is linear. This making the denominator is 1 is linear. So this is a linear program. It can be solved efficiently. So this one we have a polynomial time algorithm. So that's good. I guess the bad thing is that it doesn't give us the answer to the original question. It's going to be smaller, or it might be smaller. And the question now is like, how much smaller can it be? And so just very quickly, I'll try to explain why it can't be much smaller. And this is thanks to Bourgain's theorem on embeddings into L1. So we need another form, another version of this, where instead of minimizing over all metrics, let's minimize over what are called L1 metrics. L1 metric on V, right? So the exact same quantity. So here L1 metric just means, so i.e., there's a map. So d of xy is equal to phi of x minus phi of y, L1 norm for some phi, which takes our vertex at V and maps it into L1. Yeah, so we have these three versions of the sparsest cut problem. Right? The top one is the actual one that we care about. And then these two other ones, well, I guess you minimize over like different classes of metrics. And what we see, okay, so if we take this inequality that I wrote uh, over here, let me add to it. So we know, right, so immediately from the definitions, SC prime is the most general because it's the entire class of metrics. SC prime prime is you restrict the class of metrics a little bit, but notice that every cut metric is an L1 metric, right? Because this is an L1 metric. Remember that cut metrics looked like this. I mean, yeah, so this is a special case of an L1 metric. So we have this chain of inequalities here. And now, let me see if I can fit it here. Okay, so some basic observations are one, this is true. So it turns out that not only is every cut metric an L1 metric, but every L1 metric is some kind of positive, is a positive linear combination of cut metrics. I think this is called the cut cone representation of L1 metrics. So yeah, and one consequence of that is that the thing with cut metrics, so SC, and the thing with L1 metrics are actually uh, equal to each other. So yeah, the second inequality is actually an equality, and I'll just say this is not hard to show. If you like, think about the definition of L1, and you look at the components, and you can break it up into convex combinations of cut metrics. Um, but then the thing is that L1 metrics and metrics okay, so SC prime and SC prime prime, the way to relate these two things is to use Bourgain's theorem. Because if you are able to solve this middle one using linear programming, so you get some answer, you embed it into L1 using Bourgain's theorem, and then you get some metric here, or and right, which well gives you some like bound for SC prime prime, but then that's equal to SC, the original thing. So let's say Bourgain's theorem implies. So Bourgain's theorem, I'm embedding into L1 that SC prime prime is greater than or equal to 1 over log n times SC. And so as a consequence, we have that, sorry, I think I just wrote something wrong. There's a missing prime here. No, SC prime, SC prime, I think that's better. Yes, okay. Um, yeah, Bourgain's theorem is about relating like general metrics to L1 metrics. And if you work out whether if you take like the embedding you get from Bourgain's theorem, you get this inequality just from the definitions. Okay, so then so this gives us right, that SC prime prime is less than or equal to SC, but it's also greater than or equal to okay, constant times SC over log n. So we get an SC prime prime is actually, sorry, I feel like I'm mixing up all these primes. SC prime. Yes. Okay, so SC prime, I should give these different names. too many primes. So the one with the metrics, the one with general metrics, right? That's the thing that's easily computable, but it could be smaller than the original Sparsest Cut problem, where you only optimize over cut metrics. But thanks to Bourgain's theorem, we know that it's at most off by a factor of log n. So this is an application of metric embeddings to well, to this algorithm question. And so, and yeah, and as we remarked, this log n cannot be improved. It's not that Bourgain's theorem, but Bourgain's theorem is sharp. Right? So if we want to take this approach, then the best we can do is this log n approximation algorithm. But then later, there's this other approach. So it's a different class of metrics. So Goemans and Linial gave this a semidefinite program for as an approximation for sparsest cut. So I guess this one, I guess SC prime is referred to as a linear programming relaxation because you relax the constraint from all cut metrics to all metrics. And so here we relax it from cut metrics to a larger class as well, but not as large as the space of all metrics. So here the semi-definite program SDP is the following. So you minimize over all negative type metrics. And I'll define this on V of the same thing. It's still always the same thing. And now I don't know what to call this. How many primes? Okay. Yeah, I guess let's go with 3 primes. So there's the original sparsest cut problem, and then there's this one, and I guess two things. So I'll define negative type in a bit, but before we get there, like the reason for introducing this to this problem was that this can be computed efficiently. So it's not a linear program anymore, it's a semi-definite program, but then there are polynomial time algorithms for that. So I guess we don't need to, so that's the computer science part, I guess, or the algorithms part. Then the question is, how good is this approximation ratio for this one? Because of course we still know that this thing will be less than or equal to the actual quantity we want. And so there is a lower bound on this. This was by, so first, yes. So the lower bound is, instead of log n, it's a root log n. And this is by Arora Rao and Vazirani. I think in the early 2000s. Yeah, so here the idea was that we introduced this new class of metric spaces to optimize over. And because it's a smaller class than the class of all metrics, hopefully we have better properties. So the way Arora Rao Vazirani do this is not by a metric embedding theorem. And so that's what we're going to address today. We prove a metric embedding theorem for this class of metrics, these negative type metrics. So let me actually define that now. And so this is the like one class of metrics that we study. XD is of negative type if the snowflake of this metric, so the d to the 1/2, embeds isometrically into L2. Into L2, or I guess, i.e., there's some function phi from x into L2. Right? So a normal isometric embedding would be phi x minus phi y, L2 norm is equal to the distance between x and y. But here, because we snowflake it, we can put we put a 1/2 here. Or maybe it looks nicer to put a square here. I don't know. They're the same. Yeah. Yeah, so you can map it, you can embed it into L2, but like the relation between the distance the original metric, right? And the new L2 metric is like this. Um, mm, yeah, so I think this is one way of thinking about like where this you might wonder like why do we define this space of metrics? And at least for me, like one motivation, the primary motivation actually comes from these like computer science applications, that these are things that are easy to compute over. I don't actually know any good like geometric um like reasons for studying this like by itself. I mean, I guess it contains some special classes of metric spaces, which I'll talk about next. Um, and then I'll state what our embedding result is. But are there any questions about anything so far?
Yes. Is there some motivation for this terminology, negative type?
Yeah. So I don't remember the exact details, but I think if you look at the matrix you get, where each entry is like dxy, there's some statement about this metric, like this matrix being negative definite. Not the entire matrix, but I think on some subspace.
Mhm.
Uh, yeah, any other questions? Okay, yeah. So I guess one remark is so Arora Rao Vazirani proved this this inequality here. Okay, two things, I guess. So first thing is, if we want to follow the same kind of arguments that we did before for this inequality like, for log n, here we use the Bourgain's theorem to get this. And it's true also that if you have an embedding theorem for spaces of negative type, then you would get Aurora Rao Vazirani as like this lower bound as well. So they didn't do that. They prove a structural result for negative type metric spaces, which is enough to imply this. Uh, but the advantage of having an embedding theorem is that it actually applies to more general problems. So I stated this is like, I guess what's called Sparsest Cut for um, uniform uniform demands, uniform capacities. So this is some special case of Sparsest Cut. There's a more general version called Sparsest Cut for general demands and capacities, um, which I won't state here, but you can look it up if you're interested. And for um, that one you do need an embedding result. There's some duality theorem that for that like more general version, it's actually equivalent to like the how well the this semi-definite program for the more general Sparsest Cut, like how well this approximates the more general version of Sparsest Cut is actually equivalent to the question of like how well negative type metric spaces embed into L1. Um, so that's one motivation for studying these things. Um, yeah. Okay. So what do we know about these spaces? I guess maybe it's good to see some examples of these kinds of spaces. So examples. Uh, yeah, and this is where, so this is going to be a short list because, like I said, I don't know a good geometric like motivation for thinking about negative type spaces. But so one example is like L1. L1 is a negative type space. This is not too hard to show. So that's the first example. Second example is the Heisenberg group. So like H3, H5, H7, so on. These are all negative type spaces. I think not with the usual like Carnot-Theodori metric, but that metric is by Lipschitz to one that is negative type. And this was shown by James Lee and Assaf Naor. And these are the only examples I'm aware of negative type spaces. Um, but actually, this is a pretty good list to start with because this gives us some 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 results about these spaces. So yeah, so how well do negative type metric spaces embed into So back to the two spaces we care about, L1, L2. And so for the computer science application, we want L1 because of this well, this property here that by minimizing over cut metrics is equivalent to minimizing over L1 metrics. So we care about how well it embeds into L1. I guess just one remark, which I haven't mentioned yet, is if you have any finite subset of L2, it embeds isometrically into L1, or I guess L2 itself embeds isometrically into some L1 space. Okay, maybe not the sequence space. Let's say L1x for some x. Right, but then yeah, we always care about finite subsets of these things. So if you get an embedding to L2, it automatically can be extended into an embedding into L1 as well. So just something to keep in mind as I make the following remarks. Okay, so this is the question. And so here's some attempts at answering this question. So I think the earliest result uh, that I'll state is that due to M-flow, and this is about embedding of the hypercube, right? The hypercube is a subset of L1, and we know that that does not embed well into into L2. So I'll write it like this. There exists a negative type metric space. There exists negative type metric spaces, right, of size. For every n, there exists one of size n, such that which cannot be embedded into L2 with distortion better than constant times root log n. Right, so the example, right, is the hypercube, right? It's like 0, 1 to the like to the k, right? So n is what is 2 to the k, right? And then there's like this inflow type 2 inequality, which is exactly the statement that I wrote here. So the hypercube shows that, yeah, gives this kind of example, right? And the hypercube is negative type. Well, it's a subset of L1. Um, yeah, but so I guess up until this point, though, the thing is that for the computer science application, we care about embeddings into L1. So, so MFlow's result, uh, like there's still a chance that it could be embedded into that negative type metric spaces can be embedded into L1 better than they can into L2. It's just that you can't do it by doing, you can't do the embedding from X to L2 into L1. So even though we know we have isometric embedding here, right, because of this hypercube example, right, this one can be as bad as root log n. So you might try to go directly into L1 instead and hope for something better than root log n as the distortion. But then, okay, so Enflow's result was, I think, 1960s, 1970s. Right? But much more recently, Assaf Naor and Robert Young, this was what, less than 10 years ago, right, proved that the same is true, but with L1, with distortion better than root log n. So it's um, so the uh, so the example is clearly not the hypercube. I mean, the hypercube itself is a subset of L1, right? So they need to do something different. Um, if you just want to embed it directly into L1. And well, my list here consists of only two examples of negative type spaces. We know L1 doesn't work. So their counterexample is the Heisenberg group. Um, the interesting thing, though, is that the three-dimensional Heisenberg group, the simplest one, doesn't actually work. You have to take H5 or higher. Um, yeah, but they show that the unit ball of the discrete five-dimensional Heisenberg group, right, with the usual metric, um, cannot be embedded into L1 with distortion better than root log n. Mm. Any questions about this?
Well, you said the unit ball, but you need a finite set. So what is the?
Sorry, yeah. So the unit ball of the discrete Heisenberg group.
Yes.
Yeah. So I guess if you look at like the discrete Heisenberg group, and maybe not the unit ball, okay, ball of radius r. for every R. Yeah, thanks. Any other questions? Okay, so these are negative results. So now we know that the best we can do is root log n. And so one result in the positive direction was by Arora, Lee, and Naor about I think in 2005, 2008 or something. So this is the positive result, is that so it's similar to the form of Morgan's theorem. It's every negative type metric space can be embedded into L2 and hence L1 because of this remark up here, right? So if you have embedding to L2, you compose it with the isometric map into L1, and you have embedding to L1. So it can be embedded to L2 with distortion. At most, root log n times log n. Yeah, I guess I should put some dates here. So I think this first one was around 1970s. Naor Young was 2010s, late 2010s, and early Naor was 2000. How do you say this? The first decade of 2000, right? So um, I mean, 2000 is correct no matter how you interpret it. But the point is that it came before Naur and Young. So we had this. So there was this result of root log n times log n, and I guess like there was people weren't sure what the lower bound would be. Like maybe it's actually like root log n is not the correct power of log n. It's actually some lower power of log n. But then because of Naur and Young's result, right? Now we know that we're only off by this logarithmic factor, right? It's a log, but it's log of the main term. So yes, yeah, it's a logarithmic factor. And then the question is, so then the question becomes, can we remove this log factor? And so then that's our result. So this we posted this on the archive last year. So this is myself, Assaf and Kevin Wren. And we showed that this can be improved to root log n. So that extra log is not needed there. And like I said earlier, so this has some applications to some of these theoretical computer science questions, like these things about sparsest cut for general capacities and demands. So it shows that that thing cannot be, well, yeah. So the best you can do with the approximation ratio is root log n. Yeah. So then I guess in the remaining time, I'll say some ideas about the proof of this. Are there any questions about this? Okay, so yeah, let's move on. Yeah, and so the proof is it builds a lot on the previous ideas. So there was so I'll try to say a bit about each of these things. And so there was this like structure theorem by Arora Rao and Vazirani, which led to the proof of Aurora Lee and Naur, um, and and uh, and many of the ideas in their proofs also appear in our proof. And we make we find some improvements, like some parts where the proof can be like tightened a little bit, and that leads to this. I guess one so I guess one remark is that in between all this time, so when this proof was when Aurora Lee Naur and Arora Rao Vazirani it was published. There have been some simplifications of this proof. And so in particular, there's these series of lecture notes by Thomas Rothfuss, which simplify the argument, simplify the presentation and the argument quite a lot. And that was very helpful for us in understanding where to start in trying to improve these arguments. Mm. Oh, and also, yeah, like I said, so negative type is, at least to me, it's I not like the most natural geometric thing. And it turns out that the proof so once we proved it for negative type, we realized that it can be extended to a larger class of spaces, and so I guess that explains the title. So quasi-symmetrically Hilbertian metric spaces. That's where that's where this class came from. We look at what we had, and then realize the argument extends to this. Um, so in fact, every yeah, so here's every um, quasi-symmetrically Hilbertian metric space can be embedded. Oh, I guess so. I'll define what that means, right? But there's some modulus eta can be embedded into L2 with the same distortion. So root log n, and then now the constant depends on this modulus eta. And yeah, so what does this mean? Wait, oops, keep doing this. Yeah. So this means that the space X, so there exists a map phi. So first eta is the modulus, right? So the usual thing is that it's an increasing function on the positive numbers. Uh, and I guess usually we assume eta of 0 is 0, although we don't actually need that in our proof. I think we just need that it's less than 1. Um, and given this modulus, right, and eta quasi-symmetrically Hilbertian metric space just means that it embeds into L2 with a quasi-symmetric map with this modulus. So this means there exists a map phi from X into L2 such that, what is it? So you look at triples of points, X, Y, Z, and X. Right? If you compare the ratio of distances in the image like this, so X minus Y, X minus Z, to the thing in the domain, right? There's this inequality that relates them in terms of this modulus eta. So, so the statement is that if a space X satisfies this property here, so there is some eta for which there exists a phi such that this statement is true, okay, then you have this distortion result. And for negative type, it's a special case of this where eta is just the square root function. Yeah, so this is I think the more geometric statement behind this result. Okay, I have a few minutes left, so I guess okay, I'll try to say a few words about the proof. So a lot of the proof is so I think the general structure of the proof is similar to the previous proofs like Naor, Arora Rao Vazirani. So let me try to draw a diagram of how it works. So we have so our goal is to have this root log n embedding. And so that's our goal. And the way to get that is by proving a single scale embedding result. Which I'll state if I have time. So first we prove a single scale embedding result, and then that implies this one. And the way the implication works is you need to glue all these single scale embeddings together. I think the easiest way to glue things is to just take the direct sums, but that doesn't work here. There are too many scales. So there's this technique called measured descent, and this was by Ralph Gamer, Lee, Mendel, and Naor. And this was already used before in the earlier works as well. So the thing is that we have a slightly better single scale embedding result, which leads to this root log n as opposed to root log n times log n. Okay, and then the way we get this single scale embedding result is by so the way so there's let's say finding well separated sets, finding large well separated sets in our space. And the way this implies the thing above is by duality. like I mean like the minimax theorem. Uh, and um, and so we give some condition for how you find these well-separated subsets of your space, and this is through this notion that we introduced called I guess we say like compatibility. Let's say. Hmm. Okay, so let me state it like this. So let's say there's a structural theorem. So something about the structure of a negative type metric spaces, and more generally of quasi-symmetrically Hilbertian metric spaces. Uh, and then, so structure theorem of this implies that together with, or let me just leave it like this. Yeah, so here's our chain. So once you have the structure theorem, we show that so the negative type metric space satisfies some compatibility condition with some graph and some function, and that gives us large, well-separated sets. Sorry, this is a bunch of abstract stuff. I guess I have like 3 minutes left. So, what can I say in 3 minutes? I guess I can try to explain where this root log n comes from. And yeah, so for the details, I guess you can talk to me later if you're interested. You can look at our paper. Yeah, I'm happy to explain. But I guess I'm kind of out of time. So, I'll start with the single scale result. So the single scale result, so the single scale result looks like this. Um, and yeah, so for every scale tau, so X is a negative type metric space. For every tau, there exists a probability distribution on the set of subsets of X. So XD is a negative type metric space. Right, so 2 to the X, right, the set of subsets of X, probability distribution P, with the property that for every pair of points X, Y, with that are separated by tau, we have that if you look at this random subset Z, right, so it's chosen at random according to this probability distribution, it separates the points X and Y well, in the sense that X will be in Z and Y will be far from Z. And how far from Z? Well, our scale is tau, so the best we can hope for is tau. But there are a bunch of constants, maybe C1. And here I'll put a root log, and then there's going to be some like doubling ratio here. Ball centered around X, sorry, around Y. Uh, um, what do I want? C1 tau. Sorry, too many C's. C2. C2 tau. C1, C3 tau. Less than or equal to C4. Greater than or equal to C4. Okay, so this is some statement. And it's saying that X and Y, so this random subset that we take, right, from this random distribution, it's good at separating points at scale tau, right? If the 2 points X and Y are separated, then there's some positive probability where one will be in Z and the other one will be far from Z. Right? And then how far depends on like, the local growth of the metric space near the points near the point Y. And so this is something new that we proved. Uh, so so Arora, Lee, and Naor proved the same thing, but with with root log n instead of this thing here. And so where does this root log n come from? It Okay, so in defining these like well-separated sets, you take some random Gauss. So sorry, let me see if I can. Okay, so we have the following. It's a negative type metric space. Um, okay, so phi is negative type, which means there is an isometric map from XD to the 1/2. into L2. Right, this is isometric. So you can think of the points as sitting inside L2. And then so a way to separate them is to project them onto a line. And so you have a bunch of points, right? You project them onto a line, and then right, and you look at the images, and maybe you take like these alternating strips. So this is one subset, this is another subset. And so these two subsets are in some sense well separated. And so the way you choose which direction to project in, right, that's random. Or maybe it's easier instead of, you can think about like a random unit vector or a random Gaussian, it's equivalent. Um, but um, but when you do all that stuff, one quantity that's relevant is the following. We look at the expectation over, so let's say a random Gaussian in our space. It is L2, but I guess this can be Rm or something. Okay, so an m-dimensional random Gaussian. And so what is this kind of statement? So we take the supremum over all x in some, let's say some ball around, let's say y around. So I'll write this and then I'll say a few words and I'll finish. Let's say a scale tau. The supremum of, so the embedding, so we need points in the space. So phi of x minus phi of y. And so this is the supremum of a Gaussian process. And so there are these standard bounds on this, right? Which is what? It's the diameter. So okay, I guess you can get better bounds, but like one bound is the diameter of this ball. But remember, we care about the points as they sit inside Rn. And so the diameter of this times the square root of log of the cardinality of this ball. Well, I guess technically of the image. And so this is some standard fact about Gaussian processes. And so here we have log of this cardinality, but the cardinality is bounded above by n. And so that's one way to think about where this root log n comes from in all of these arguments. And so then the idea is that can we do something better than log n? Can we get that doubling ratio that we want? And the idea is yes. And we don't use this map phi anymore. So this map phi comes naturally because we know our space is negative type, but we actually can apply this projection not to phi of the points, but to some other map where we first round the points to nearby points, and this has an effect of compressing the cardinality of the images of these balls, right? So the balls themselves, there's some cardinality that we can't bound, but the images of those can be bounded after this compression by this local growth. So I guess that's at least one idea of some geometry that goes on in this proof, but I'm over time, so I'll stop here. Thank you.
Okay, thank you. Yeah, let's thank Alan. So are there comments or questions?
I have one question. So do you need the full full function eta, or is some kind of weak quasi-symmetry enough? And so
Yeah.
is it enough that you say you have some delta epsilon type quasi-symmetry that if
Yes.
the ratio is less than delta, then on the image side you're less than epsilon?
Yeah, that's all that we need. And so yeah, so it's something like right, if this thing is less than delta, then this other thing is, like you said, is less than epsilon. And
Yes. You just need two values that are less than
yes.
one, both of them.
Yes.
Yeah. So they're just very weak quasi-symmetry.
That's all we need in our proof.
Yes, that's yeah. I cheated a little because I had seen Assaf talk about this. So I recalled this, but just checking if I remembered correctly. Thank you.
Yeah. So I think like it's, at least to me, it makes the proof more complicated, like in this general case. So like the way, for me, it's helpful to think about how we found the proof, which was we started with negative type and then we extended it more and more, and we realized, oh, we don't need this, we don't need this, we don't need this.
Maybe one comment for this audience, you didn't say this, but it can be helpful for some people here, that it was also an earlier result. It's almost immediate. Well, depends how you think of it. If the metric is doubling, then any doubling metric space automatically quasi-symmetrically embeds, and you get this O log n, square root log n. Of course, the quasi-symmetry depends on the doubling constant, so you get some hidden dependence on that. But that's of course also known classically, so you can just prove it. If the metric is doubling, you can just adapt Aswad's proof to give you O square root log n type embedding. So that, yeah.
Yeah, so I'm
That might be a more speculative question. Is there somehow some connection between, or do you see some connection between this kind of Aswad's argument that works for doubling spaces and your argument that now works for these quasi-symmetrically Hilbertian spaces? Maybe this is a ill-posed question.
The connection between the two arguments, you're saying?
Yes, yeah.
Yeah, that's a good question. Yeah, but I don't know. I would have to think about it more.
Yeah. Thanks.
So let me ask you a clarifying question, right? I mean, so you explained where this log n term comes from, right? At the very end here, right? But you're saying, I mean, the estimate that you write down there in some sense is not optimal, right? I mean, so I guess if you use just this estimate, then you acquire some extra terms, and what you did, you modified this approach to somehow just get the square root log n term. Is this the right way to think about it? Or?
Yeah. So here, so in the original arguments, so in all these arguments, it involves some quantity like this with some map phi. And the most natural map phi to take is you just take your space and you use the negative type map that you're given, right? This map phi that comes from the negative type definition. And so what we did was we don't take this map phi directly. We have some rounding procedure.
No, I understand what you said about this, but I'm just trying to get to the, you said in this estimate that you wrote, this square root of log term essentially explains the square root log n, right?
Yeah.
But you're saying, I mean, then you get some other kind of error, right? Because there was this log n term in the original.
Yeah.
You have some loss somewhere else, right? So you get the square root log n, but then you have some loss somewhere else.
So that comes from this like this part here, this measured descent technique. When you apply it with the square root log n for the single scale embedding, right? If you have a square root log n here, and then you try to go from this step with a square root log n to here, you pick up an extra log n.
I see. But
yeah, and so it was already known before.
Now gets rid of this extra term, right?
Yeah, so I think it was already known by these people that if you were to prove some kind of like result like this, then this would imply that because it's the same argument.
Okay, other comments or questions?
Yeah, I have a question. It might be very elementary, but could you go back to the definition of the negative type spaces?
Yeah.
So if one tries to do, it seems that one tries to snowflake the space and asks whether it embeds isometrically into L2 or not. Does it make sense to define a space where you snowflake it by 1 over P and embed that isometrically into LP, and then try to see what's different with those kinds of spaces? Or is that somehow elementary trivial?
So you're saying like transposing Q's to P's?
Basically, yes. Yes.
Yeah, so I'm not sure how. So I haven't looked into it. I haven't like heard anything about those things. I guess the thing is, yeah. So here, and I think for me, like this, it doesn't seem to me like this is a very geometric type of condition, and when we first started working on this, to me, it seemed like this 2 here and this 2, it seemed like there's something special going on, right? The fact that they were the same. But then the fact that our proof like works more generally, like it seemed like like the L2 norm and this square or the square root, I think it just came from the theoretical computer science application, because like the actual embedding result, you don't need, okay, right, we talk about embeddings into L2, but you don't need this to be a 2 here.
I see. You could snowflake with a different exponent, I guess, and still ask about L2, which is
Yes,
sort
yeah.
of
So then our more
That's-
general statement, this quasi-symmetric version, right, will apply for that. Yeah, but if it's for LP, then I'm not sure.
I see. Okay. Thank you.